Okay, so in this section we are going to define the definite integral. And the definite integral is this thing that we've been talking about that gives the area under a curve over some interval. We usually use AB as our interval. Okay, so let's go ahead and write down the definition. So given a function on an interval, so here we have the closed interval from a to b, then the definition of the definite integral is going to be what I was referring to in class, and I think in the last video, it's going to be the limit of the Riemann sums. So the definite integral of a function f from a to b is the integral sign. So remember, we saw this before, but here we're going to have numbers at the top and the bottom, and those are going to be our bounds. So similar to how we have bounds on a summation or a sigma notation when we write a sum. These bounds tell us when to start and stop, and because we're integrating over the interval a to b, that's why we have a at the bottom and b at the top. And then we have the function f of x, and again we have that dx that indicates the variable, right? Okay, so we take the limit as n goes to infinity of the Riemann sum. So this is what we were referring to before, saying that we take the number of rectangles. Remember, we referred to that using n. We take the number of rectangles to infinity and get a better and better approximation that in the limit gives us the exact answer. So remember that our Riemann sum, I was writing I guess I'll write it in the same way, so I need a little bit of space. So we had the sum of all of the heights of the rectangles, and then we multiplied that by delta x. And so this limit is of this entire thing. Notice, okay, so we're taking a limit as n goes to infinity, and the place where n shows up is up here. It's actually also wrapped up in this notation here, the xi stars, because of what a Riemann sum is. So actually, f of xi star does depend on n, even though it's not immediately obvious from the notation. Like there's not an n in that sum right away. But when we do actual examples, we'll see that the n does appear in there, and so it'll be a little more obvious what this limit, or how to approach this type of limit. Okay, so let's just note that delta x is always b minus a over n, and xi is the ith endpoint, right? So we usually start, so we did this before, but we start at a, that's x0, and then we jump by delta x to get to x1, and we keep jumping along, and when we get to xi, that is going to be a plus I jumps, so I times delta x. And so that's where we get this formula for the value of xi. And remember that xi star was a sample point chosen from the ith interval. And then if this limit exists, because remember that sometimes limits might not exist. So we do need to check when we actually apply this to a real function that the limit does exist. And if it does exist, then we say that the function f is integrable on the interval a to b. So it is important that we note the interval from a to b because a function might be integrable on one interval but not on another, depending on what kind of function you're looking at. And the other thing I was going to say is that this is really similar to when we first defined the derivative, and we said that a function was differentiable at a point if the limit that we used to define it did exist. And so this is a similar idea, but when we're talking about integrals, and in particular definite integrals, we have to be talking about a certain interval. So a function isn't really integrable at a point. We don't talk about that because it doesn't give us much information at all about the function. What we do want to talk about is the, because we're talking about the area under a curve over some interval, for that to be interesting at all, we need some width, right? Some interval on which to look at the function. Okay, so now I'm just going to give you some formulas that we are going to need, and we're not going to derive them, but I'm just going to let you know what they are. So they just involve some clever ideas that simplify these particular summations really nicely. So the first one is summing I from 1 to n, and this is, the formula is n times n plus 1 over 2, right? And that's your formula. Okay. The second one is going to be the sum, or the sum from I equals 1 to n of I squared. This one is n times n plus 1 times n plus 2 over 6. And from I equals 1 to n of I cubed, this one is n times n plus 1 over 2 squared. Okay, now notice that when we, so what's nice about these formulas is that we go from having this summation to having just a formula in terms of n, which is just the number, well, in our case, it will be the number of rectangles, right? So moving from this sum to something that looks like this makes it a lot easier to deal with, and so we are going to be using these quite a bit. Notice that there is a squared on this one, so don't forget about that when you're using the formula, because it can be easy to miss it. And it is the entire thing being squared, so it would be n squared, n plus 1 squared over 2 squared if you were to distribute the exponent. Okay. And then a couple properties of sums that we're going to be using. These just come from the properties of addition, so they should be pretty, they should make sense at least. So the first is that if we have c times ai, that we can pull that c out. So if we have a factor that appears in each term of our sum, we can pull it out. So that is exactly what's going on here. And then if you have the sum from 1 to n of ai plus bi, we can rewrite this as the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi, right? And so this would just involve arranging the terms, and we know that we can do that with addition, so no problems there. And then it works the same way for if you have ai minus bi. We can split this into I equals 1 to n of ai minus sum of bi, right? And then lastly, this was something we touched on just a little bit in the last section, But if you sum a constant n times, so if you take c plus c plus c and you do this n times, whatever n happens to be, then what you'll get is n copies of c, which we know is just n times c. Okay, so that is also helpful. Okay, so I'm going to stop here and we are going to do an example of computing a definite integral in the next video.